So for the first one, we have just f of x is equal to x cubed, just like the one above. So you can go ahead and try to think about, where do we start? We start at 0, 0. We go right one, up one, because 1 cube, it's 1. And then 2 cube, it's 8. So that's why we go right 1 and then up 7. You move in the opposite direction on the other end. So what you will find is that you will find a graph that is pretty darn narrow. Okay, it is pretty darn narrow. It's okay. Now, when you draw your cubic function, I hope you can focus on one thing, and it is going to be right here. Okay, now this is going to be pretty crucial, not just for now, but when we do polynomial graphing later on this semester and in pre-calc, I want to make sure that you recognize this kind of turn. Now, what I call this turn is like an S-shaped turn. Okay, so that's what it looks like when it's a cubic function. Okay, so try to create this turn when you draw your graph. Okay, so center of rotational symmetry, like your quote unquote starting point, that's going to be your 0, 0. Domain and range, it gets boring time after time because it's always going to be from negative infinity to infinity. The x-intercept in this case would be 0, 0. And that would be the same thing as your y-intercept. So this one's kind of boring. That's all right. Okay. Yes. Now, I would put a quote unquote on the vertex. There's no vertex here. Vertex means the turning point, right? So, so in this case, the h and k represent something, and it will represent the center of rotational symmetry. Okay, so that's a good point. So, so when we did quadratic equations, the h and k represents the vertex. When we do square root function, the h and k represent the starting point. And now for cubic function, the h and k represents the center of rotational symmetry. Okay, so now let's go ahead and look at the second example. Okay, let's look at the second example. What does this minus 2 mean? It moved down 2 units. So that means originally we start right here, but now it's being shifted down 2 units. Okay, and that's the only transformations that we have here. So we're good. So we can start right there and do our counting. All right, right one up one, or left one down one, and then it goes up 7 units. So -1 goes up 7. You have a number at 6. And -3 goes down 7. You have a number at 10, -10. Okay, so that's how you will have the drawing. Okay, the y-intercept is very easy. 0, -2. Now, I want to put a little bit of emphasis, so I'm going to put a star next to x-intercept. All right, so what's the x-intercept right here? If you zoom in, you're like, is it like 1 point something? And a very common question that student would ask is, hey, Mr. Chen, so do we just approximate the number? And the answer is you don't, okay? Now, let me ask you something. What do we know about x-intercept for sure? What do we know? Yes. Y is always 0, right? So how can we find out the x value? Well, you've got the equation, don't you? This is the equation. So what you would do is that you put y equal to 0. And now, ask yourself, would you know how to find out x by itself? What would you do to get x by itself? You would first add 2. How do you get rid of the cube? You could do something called louder cube root. So you can just go ahead and cube root both sides. And that's the power of understanding what inverses are. Cube root is the inverse of cube. They cancel each other out. So you have x by itself, and on the other side, you have cube root of 2, and we write down cube root of 2. That's it. That would be the exact answer. Now, if you're curious about what that number is, you can go ahead and use a calculator to find out what the number is as an approximate. But this is how we would express our x-intercept when a number is not very nice. All right, are we good? Okay. Okay. So that would be the case for x-intercept or y-intercept. If a number is not like a clean cut, not a nice number, what you would do is to go ahead and substitute and find out what it is.